Hello everybody, welcome into another lesson. So today we are going to talk about continuity of a function, and then we're going to talk about discontinuities. In particular, for today's lesson, we're going to talk about removable discontinuities. So what does it mean for a function to be continuous? Well, graphically, it's best to illustrate it like this. If I can take a marker, a pen, or a pencil, I can draw a smooth continuous curve without ever putting down my writing utensil. If I can do that, without ever having to lift it, if I don't ever have to lift my writing utensil and I can draw a smooth continuous curve, the function's continuous. That's graphically what we're looking for. If you don't have to lift your writing utensil and you can draw the thing all the way through, it's continuous. Now, algebraically, what does that mean? That means that the function is defined for all values in it, that the function is defined for all values in its domain. That, like for a polynomial function, for example, it's defined for all real numbers. So polynomials are continuous through the set of all real numbers. And this idea that when we apply it to limits is, if a function is continuous at some point a, then the limit as x approaches a of f of x equals f of a. So if the function's defined at this point a, then the limit as x approaches a of f of x equals f of a. That's where the idea of direct substitution comes in for solving limits. And you'll often have a problem like this when it pertains to continuity. You'll see something like use continuity to evaluate the limit. So we're going to do a few of these. We're going to use continuity to evaluate the limit. And let's say we have something like the limit as x approaches 4 of that 5 plus the square root of x all over the square root of 5 plus x. So we're going to use continuity to evaluate the limit as x approaches 4 of 5 plus the square root of x over the square root of 5 plus x. Well, if we look at this function, it's defined when x equals 4. We don't even need to use rationalizing or any of that. We can do direct substitution because this function is continuous when x equals 4. So let's just use direct substitution. If you put in 4 for x, you would end up getting 5 plus the square root of 4 all over the square root of 5 plus 4, which would turn into 5 plus 2 over the square root of 9, which would give you 7/3. So the limit as x approaches 4 of this function is 7/3, and we were able to use continuity to evaluate the limit since the function is defined when x equals 4, and use direct substitution as a result. We get 7/3 for our limit. I got 3 more of these, and then we'll get into the first type of discontinuity today. All right, the limit as x approaches pi of the sine of x plus the sine of x. What a function. So we're taking the limit as x approaches pi of the sine of x plus sine of x. Well, let's break this down here. Let's go inside the parentheses. Sine of x is actually defined for the set of all real numbers. X certainly is too. It's technically a polynomial function, so that means the sign of that quantity is going to be defined. We can use continuity to evaluate the limit, which means we can do direct substitution. So let's input pi in for x. You'll end up getting sine of pi plus the sine of pi. Well, work inside your parentheses. What's the sine of pi? It's 0, so you would end up getting the sine of pi plus 0, which would just turn into the sine of pi, and the sine of pi is 0. So using continuity to evaluate this limit, which enabled us to use direct substitution, we get the limit that as x approaches pi of the sine of x plus sine of x is equal to 0. Two more of these. We have the limit as x approaches 1 of e to the x squared minus x. Alright, well, so the limit as x approaches 1 of e to the x squared minus x. Well, e is defined for the entire set of real numbers, and so is the polynomial that it's raised to, so we can use continuity, which would enable us to use direct substitution. So let's put in 1 for x. You would get e to the 1 squared minus 1, which gives you e to the 1 minus 1. That gives you e to the 0, which would just give you 1. So the limit as x approaches 1 of this function is going to be 1, based on using continuity to evaluate the limit. I got one more of these. This one's a good one in my opinion. The limit as x approaches 2 of the arctangent of x squared minus 4 all over 3x squared minus 6x. Well, we haven't seen the arctangent function since pre-calc, so this is some very good news this is very good that we're seeing this, because we haven't used arctangent in a while. But let's look inside the parentheses first. If we input 2 into the denominator, are we going to get an undefined value? Well, 2 squared is 4, okay, so 3 times 4 is 12, minus 6 times 2, that's 12, that's 0. Well, it's not always direct substitution that we use. We can also use factoring, which would then enable us to use substitution, or you can use the conjugate method. The three methods that we learn to evaluate limits are based on using continuity to evaluate the limit. Now, I know we can factor inside of the parentheses in the arctangent function, so let's do that. This would give you the limit as x approaches 2 of the arctangent of, I'm going to put brackets here because both the numerator and denominator will factor, that x squared minus 4 would turn into the quantity of x plus 2 times x minus 2. The denominator, you can factor out a common 3x. This would turn into 3x times x minus 2. Well, now we notice you have a common x minus 2 that'll cancel out. So this would turn into the limit as x approaches 2 of the arctangent of x plus 2 over 3x. Alright, so now what we have here is the limit as x approaches 2 of the arctangent of x plus 2 over 3x. Well, the good news is we're not going to get anything undefined inside of the brackets. And also good news is the domain of the arctangent function is the set of all real numbers. It's continuous at x equals 2, so we can use direct substitution to evaluate the limit. So let's do direct substitution. This would give you the arctangent of 2 plus 2 over 3 times 2, which would end up giving you the arctangent, which would be 4 over 6, which is really 2/3. So let's go ahead and see if we can find a decimal approximation. I had to get my handy dandy phone, which is actually my handy dandy calculator. So let's take the arctangent of 2/3 and round it to 2 decimal places. Alright, it's in radians, good. So let's see. The arctangent of 2/3 would be about 0.59. So the limit of this function as it approaches 2 is approximately 0.59. So yes, eventually you may get to direct substitution, but sometimes you may have to use factoring or the conjugate method to get there. But those 3 methods we previously learned for dealing with how to evaluate limits are all based on continuity of a function. Now, there will be times, unfortunately, where a function is not continuous. This is really going to be the focus of the next 4 lessons. We're going to talk about types of discontinuities. So, discontinuities, as you can imagine, means, simply put, the function is not continuous. There are 4 types of discontinuities. One is called removable, which we're going to talk about today. Removable discontinuities is the topic of today's. In the next lesson, we're going to talk about jump discontinuities. In the 3rd lesson, we'll talk about the next 2 types of discontinuities called infinite and endpoint. So today's is about removable discontinuities, and you're going to see why we call them removable. The next lesson's jump discontinuities, and then the lesson after that will be both infinite and endpoint discontinuities. And then the 4th lesson is going to be called crazy graphs, where we combine all these into one, and you have to identify where the function's continuous or not, if it's continuous from the left or right or neither, and then what type of discontinuity is it. So that'll be the topic of the 4th lesson. But today, let's dive into the removable discontinuities. Let's start out with a graphic example of a removable discontinuity. So let's say I got some line, except right here I have a hole. I have a hole right here in the line. If you see a hole in a graph where it's not defined, that's what's called a removable discontinuity. A hole is a removable discontinuity. That means it can be removed, simply put. So if you ever are seeing any type of curve, it doesn't just have to be a line. Like, let's go ahead here, I'll draw another one. let's say I have a parabola. I'll draw one with a parabola even, but you have some value where there's a hole in it. That is a removable discontinuity. It's not defined there, but it's defined everywhere else except for that particular value of x or that value of y that comes from that x. So that's graphically what a removable discontinuity is going to look like. Now, what type of function produces a removable discontinuity? That's going to actually occur quite often when you have rational functions where you can factor out either the numerator or denominator. And we've encountered those when we were dealing with the factoring method for evaluating limits. Those actually were all removable discontinuities. So let's do an example here. Let's say I have f of x equals, let's do x squared minus 1 all over x plus 1. So I have f of x equals x squared minus 1 over x plus 1. I think it's plain to see that we can definitely factor out an x plus 1 from the numerator and denominator. So in fact, let's factor the numerator. This would be the quantity of x plus 1 times x minus 1 all over x plus 1, which would just simplify into x minus 1. So you're going to have a line. You will have a line here of y equals x minus 1. This is simplified into f of x equals x minus 1. And you're going to graph the line accordingly, except x cannot equal -1. It's not defined at -1 because you have to go back to the original function. If you input -1, you'll actually end up then having a 0 denominator. So you can say there is a removable discontinuity at, you want to find the point. So take that x equals -1 where it's undefined, and you're going to input it into the new function that you got from factoring. That would be, if you put in -1 here, you would end up getting the point -1, -2. So there is a removable discontinuity at the ordered pair -1, -2. Let's graph that. So I have the line x minus 1. So let's see, let me just graph some points here. All right, I think we got sufficient points going this way to graph. And then now if we go to 0, -1, let me put blue ink there. Actually, let's do red ink so it stands out. At -1, -2, there is your removable discontinuity. I have a red circle there that's not filled in. But everywhere else around it's continuous, except for literally at that point -1, -2. That indicates a removable discontinuity there. We'll get into how to remove a discontinuity. So again, these happen when you have rational functions where you can either factor the numerator and denominator to form a new function, or I should say, and then you want to find where the original denominator was undefined. You take that value of x, put it into the factored version of your function, you'll get the coordinate of the removable discontinuity. So you just have a normal graph with a hole at that point. Let's do another one where you have a removable discontinuity. Let's say this time I'm going to do f of x equals x cubed minus 1 all over x minus 1. So I'm going to graph f of x equals x cubed minus 1 all over x minus 1. Well, this is a rational function again, but I think we can see that the numerator is going to factor. That's going to factor into x minus 1 times the quantity of x squared plus x plus 1. All that divided by x minus 1. Well, now your x minus 1's factor out. F of x is now just simply equal to x squared plus x plus 1, except you have to go back to your original equation where the denominator was, set x minus 1 equal to 0, you would get that x equals 1, so x cannot equal positive 1. X is not defined at x equals 1. That means you have a removable discontinuity at what ordered pair? So go ahead, put in x equals 1 into this factored function. You put in 1, so 1 squared is 1, plus 1 is 2, plus 1 is 3. So you have a removable discontinuity at the ordered pair 1, 3. Now let me go ahead here and put that as a red dot to indicate our removable discontinuity. This is going to look like a parabola with a hole in it at 1, 3. So if I put in 0, I would get the ordered pair 0, 1. If I put in 2, so 2 squared is 4, plus 2 is 6, plus 1 is 7, will be all the way up here at 2, 7. If I put in negative 1, so that would be 1 minus 1 is 0, plus 1 is 1. Yeah, negative 1, 1 minus 1 is 0, plus 1 is 1. And then if I put in negative 2, so that would give me 4 minus 2 is 2, plus 1 is 3. Let's find the vertex. The vertex, of course, is negative b over 2a. So the vertex, the x-coordinate is going to be negative 1/2. So if I put in negative 1/2, I would end up getting 1/4 minus 1/2 is negative 1/2, plus 1 is positive 1/2. So that'd be at negative 1/2, positive 1/2 for my vertex. There's my vertex of the parabola. So now let's draw this curve, this parabolic curve. And notice I have a graph of a parabola, except I have a hole in it at the point 1, 3. That's the removable discontinuity. So again, rational functions with a factorable numerator or denominator that causes factors to cancel out will create a removable discontinuity. So then you, of course, you completely factor the function, and then you go back to your original function where the denominator was 0, set your denominator equal to 0, you get the point of x where it's not defined, plug that into your new function, you'll get the ordered pair where the removable discontinuity is. Alright, now, we want to talk about removing the discontinuity. It's called removable for a reason because the discontinuity can be removed. So let's see here. Let's say I have the original function f of x. Let me write down what we're doing here. Removing the discontinuity. So sometimes you may be asked to remove the discontinuity and define it at that value. It's actually super easy. So let's say f of x equals x squared minus 4 all over x plus 2. So you have the function f of x equals x squared minus 4 all over x plus 2. Well, I think it's safe to say we can factor out the numerator. This would turn into the quantity of x plus 2 times x minus 2, all that divided by x plus 2, which would end up giving you that f of x equals x minus 2. You'll end up with f of x equals x minus 2, a simple line. But if you set your original denominator equal to 0, you'll get that x cannot equal negative 2. X cannot equal negative 2. The discontinuity is going to be at the ordered pair then negative 2. So input that negative 2 into your new function. Negative 2 minus 2 is negative 4. So the removable discontinuity is at negative 2, negative 4. Let's go ahead and graph this first. So let me find negative 2, negative 4. I'm going to put a red hole there to denote that that's a removable discontinuity. All right, so at negative 1 you would get negative 3, 0 you would get negative 2, 1, negative 1, 0, I'm sorry, 2 you get 0, 3, 1, okay. Let's see, negative 3, negative 5, negative 4, negative 6. I'm just drawing sufficient points here to graph this. I want to show you why we're removing the discontinuity. Because sometimes you're also going to be asked to graph it. So as you see, I have the graph of x minus 2 with that removable discontinuity at the point negative 2, negative 4. Now, removing the discontinuity, what you need to do, you're often going to set up a brand new function. So we'll call this new function g of x. What you do is you make it a piecewise function. So you take your factored form of the function x minus 2. It's equal to x minus 2 when x is not equal to negative 2. We keep that because if you look at this, that's true. The function is equal to x minus 2 everywhere except x equals negative 2. In order to remove the discontinuity, the second part of the piecewise function is going to be negative 4 when x equals negative 2. You need to define it for your y value of negative 4 when x equals that value of negative 2. Once I do that, I have removed the discontinuity. I now have a solid dot there and created a continuous curve. So yes, this would be treated like y equals x minus 2 everywhere except x equals negative 2. But y is not defined at negative 4 initially because that's where x equals negative 2, y would be negative 4. So then you say it's defined at negative 4 or equals negative 4 when x equals negative 2. So you create a piecewise function where the second piece is it's equal to the y value of the removable discontinuity at the x value of that removable discontinuity. And then you've just created a smooth continuous curve. Let's go ahead and do another one. So let's see here. We have f of x equals, all right. Let's do 27x cubed minus 8 all over 3x minus 2. So we have f of x equals 27x cubed minus 8 all over 3x minus 2. Well, okay. So we can definitely see this is going to factor out. So let's factor the numerator. That would turn into 3x minus 2 times the quantity of 9x squared plus 6x plus 4 all over 3x minus 2. So your 3x minus 2's cancel out. This now turns into a quadratic function. F of x equals 9x squared plus 6x plus 4. Except we have to look at where the denominator of the original equals 0. If you set 3x minus 2 equal to 0, you would actually get that x equals 2/3. So it's not defined when x is equal to 2/3. So where is the discontinuity? Let's put in 2/3 into this brand new function. If I take 9 times 2/3 squared plus 6 times 2/3 plus 4, well, that's going to give me 9 times 4 over 9 plus 6 times 2 over 3 plus 4. So 9 times 4/9, that's going to give me 4 plus, all right, 3 cancels into 6 2 times, so you get 2 times 2 is 4 plus 4. You end up getting 12. So there is a removable discontinuity at the point 2/3 12. So the discontinuity is at 2/3 12. Also, for good measure, let me find the vertex. So x equals the negative of b over 2a, so negative 6 over 2 times 9 is 18, which would be negative 1/3. Let me find my y coordinate. So 9 times negative 1/3 squared plus 6 times negative 1/3 plus 4. Well, that equals 9 times 1/9 minus 2 plus 4. So that equals 1 minus 2 plus 4, which would equal 3. So my vertex is located at negative 1/3 3. All right, now that I got the discontinuity point in the vertex, I can draw a good graph of this. That's my goal. I want to graphically show you what's happening. So, vertex negative 1/3 3. I'm going to make each of these y units count for 2. So, negative 1/3 3 is right about there. And then 2/3 12. Whoops, I need the red ink because that's where the discontinuity is. So about 2/3 12 is about right there. So we got the vertex, we got the discontinuity, so here's about what your graph is going to look like. With that discontinuity in the parabola. So there's my parabola graph with that discontinuity at the point 2/3, 12. Now, we want to remove the discontinuity. We want to make this a continuous curve. So how are we going to do that? So set up a new function g of x, set up a piecewise function where it equals that 9x squared plus 6x plus 4, where x does not equal 2/3. But in order to remove the discontinuity, we need to define it for that y value of 12, so it'll equal 12 when x is equal to 2/3. By doing so, we have just removed the discontinuity and made this a continuous curve. So that's how you would remove a removable discontinuity. Now you see why it's called removable. And that's actually it for this lesson. Next lesson, we're going to go on to jump discontinuities. We'll explain what those are, what those graphically look like, and believe it or not, we can also find values of a function that would make it continuous. So I hope everybody has a great day. Take care.